So in this last section, I just want to make a few remarks and talk about this whole topic of cosmological tensions, which is very much in consideration in the literature at the moment. So I've given you half of the story, or at least the way that I would express it. Previously, you would read discussion of the S8 tension, and that's just the offset between the galaxy for all laser pointers coming up. Never mind. It's okay, I can point with this. Oh, yeah, good, thank you. Realize there's a mute switch on it. So in the galaxy we share world, there's much discussion of the S8 tension, and mostly that has been implicitly thought of as a difference in normalization. And you can tell that by the definition for S8, which let me remind you is sigma 8 with a correction term depending on the density scale to a fiducial value of earlier matter. So you can tell from the way that's constructed, because there's no scaling to a fiducial value of sigma 8, that it's the galaxy shear people thought of this as a primarily a measure of the normalization of the Bayer spectrum. And if that was so, it would be very interesting in terms of dark energy or theories of gravity, because it would have indicated that the growth in the density fluctuations between the last scattering, when we read off the Planck amplitude, to the present, was less than in the standard model. So gravity had become weak, for example. That's a very exciting possibility. But as I tried to emphasize, when you include the results from CMB lensing, you can actually turn this tension into what I would regard as a density tension, a density parameter tension. The question is, do you prefer the lower density parameter that gravitational lensing seems to want consistently, or do you prefer the high Planck value? All right, so let's keep that in mind, but let's talk about other cosmological tensions. And probably you all know which one I have in mind, which is the Hubble constant. And if everybody's familiar with this, it's received a lot of discussion over the last 3 or 4 years, which is that there are two schools of thought. You can either have the Hubble constant that comes from Planck, which is S pi value is about 67, or if you look at the traditional approach to estimating the Hubble constant, which is to build up a distance ladder from absolute and relative distance indicators. So, the relative distance indicator is supernovae. This is worth emphasizing, really, that what we measure very accurately is apparent magnitude versus redshift for supernovae that has some well-defined locus, and its shape tells you about the expansion history. So things like the density parameter, the size of the cosmological constant, but it doesn't tell you about the Hubble constant, because all the Hubble constant does is move the locus up or down, because it scales the absolute value of distances, but you can't predict the absolute magnitude of supernovae, so that needs to be calibrated somehow. And so the absolute magnitude comes from Cepheids. So that is, there's some range of redshifts at the low end of the Hubble diagram where there are galaxies where you have Earth-Cepheid distances, and there are supernovae. So there are galaxies which contain supernovae where the absolute distance can be calibrated. All of that, traditional approach, but using modern data, gives you a Hubble constant of somewhere around 73. And so, in terms of statistical significance, there's no doubt that this is a colossal gap. So, yeah.
I didn't understand that part where we calibrate the Hubble.
Okay, good. Let's put it another way. Rather than talking in terms of magnitudes, let's talk about fluxes and luminosities, the same apart from working in log units. So, I have the flux coming from some distant object. Is its luminosity divided by the luminosity distance squared. And the luminosity distance scales according to the Hubble distance length as redshift plus things that are quadratic and higher, and this is where the matter density lives in these higher order corrections. So at low redshift, there's no dependence on density. The distances are simply proportional to the Hubble constant. Okay? So you might well, at low redshift, you might well measure f proportional to 1 over z squared. So z very much less than 1. But that doesn't tell you what the Hubble constant is, because you need to know the absolute luminosity. All right? Whereas if you have any case of an object where the actual distance is known, so by a piece of advanced mathematics, we turn this into L equals F times D squared. Okay, so if you have a few low redshift objects where the distance is known directly from Cepheids, which in themselves are objects of, in principle, unknown luminosity. But the point is that Cepheids can be observed close enough to us that we can get direct geometrical distances by parallax from the Gaia satellite. So in principle, we can calibrate the absolute luminosity of Cepheids. They tell us the distance to a particular nearby galaxy that contains a supernova. We calibrate the luminosity, and then we know the constant of proportionality that goes into this relation. And that tells us the Hubble constant. I mean, actually, you might wonder why do I need very many objects? Because if you look at this relation, so let's write it again. For very small redshift, the flux is equal to the luminosity divided by C on H naught times Z squared. Well, that's not actually, we don't need all that. Let's just look at this. So it just says that if I go to small redshifts, it just says that H naught is equal to CZ divided by D. So if I have one object where the distance is known, apparently I can read off the Hubble constant. A single object will suffice. The problem, though, is that when the redshifts are small, peculiar velocities come into play. So the redshift is approximately the cosmological redshift, which is h0 times distance divided by c, plus peculiar velocity. So because structure is forming, if you have the cosmic web, material has to be flowing onto the high density regions of the web in order for matter to accumulate. So there must be additional velocity fields beyond the Hubble expansion. And we know these velocities are, say, 500 kilometers a second. So in order to play this game, you would need to know the absolute distance to an object whose recessional velocity, whose cosmological recessional velocity is very large compared to 500 kilometers a second. And in practice, you can't do that with individual objects, which is why we have to do this kind of two-stage process, reaching to very high redshifts with the supernovae, and then extrapolating back to local distances. Okay? So all that, there's a long tradition of trying to measure the Hubble constant this way, and it ought to work. So it's kind of puzzling that we have this larger number. So what does one make of this? The striking thing is that this Hubble constant from Planck is not a direct measurement. What we're doing is learning about the properties of the universe at a redshift of 1100, and then we rely on the cosmological model framework built on Einstein's theory of relativistic gravity, and the assumption that the matter content is dark matter plus baryons plus the cosmological constant, and then we extrapolate all the way from redshift 1100 to the present to predict the Hubble constant. So this early universe value of h0 depends on all those model ingredients being correct. And so a lot of people look at this disagreement and say, obviously, therefore, we have to modify the cosmological model in some way. All right, well, before getting into what that might be, you ought to be, if you don't work regularly in this field, you ought to be saying, well, okay, now we understand roughly how a combination of data on standard candle objects like cichlids and supernovae can tell us about the Hubble constant. How do we get the Hubble constant out of the cosmological right way background, actually? So I want to say a few things to try to clarify that. And the short answer is through Baryon Acoustic Oscillations. So this is the first time I've actually shown the sky distribution for temperature fluctuations. I'm sure you've all seen this before now. And here's the actual power spectrum rather than my sketch of it. So the substantial peak at a wave number of 220 means it exists because the temperature distribution, although there are these substantial large angle fluctuations, basically this is quite a spotty distribution, and the little spots are about 1 degree across, and that represents structures of this particular scale. So what is that scale? Why 1 degree and not 1,000th of a degree? It's because there is a characteristic length scale in the early universe, which is set by how far sound waves can propagate. And this is called the acoustic horizon. And in co-moving units, this is just the speed of sound. Well, how far can the sound wave get at a given time? It's speed of sound dt but then you divide by the scale factor to convert that into co-moving length. It's almost always working co-moving length units. As I said just before the break, for a large fraction of the early evolution of the universe, baryons and photons are coupled together very strongly by Thomson scattering. And that gives that combined fluid the speed of sound, which is actually c on root 3. You might wonder why root 3, and the answer is actually pretty easy. You might remember remember your kinetic theory. Pressure equals a third rho v squared bar. Yes? Remember that 1/3 just from averaging over directions of the particles in a gas. So it's that same, so the speed of sound is driven by the pressure. It's that same 1/3, or the square root of it, that appears here in the speed of sound. So the acoustic horizon is smaller than what you would generally talk about the causal horizon, that is how far can light signals be exchanged, but it's close to it. And so if you calculate this at the time of last scattering, it's a bit under 400,000 years, it turns out to be a length scale of somewhere around 150 megaparsecs. And I'll show you a more detailed formula shortly. But basically, you take 150 megaparsecs at the co-moving distance to last scattering, where the conventional number is about 13 gigaparsecs. And that gives you this characteristic scale, angles intended of about 1 degree. So what you're seeing here is that on scales larger than that acoustic horizon, baryons and dark matter are unable to separate, but on smaller scales, they do separate. So you imagine a spherical blob of mass that's trying to undergo gravitational collapse. Well, after a while, the pressure in the baryonic component will resist the gravity, and actually, rather than just continually falling in, the baryons fall in and they bounce. And so, depending on where you catch them in that bounce, that acoustic standing wave, you see peaks and troughs in the temperature distribution. Now, the interesting thing is that you also see those same acoustic oscillations in the present-day matter distribution. So this is worth talking about in a little bit of detail. And you can understand this by what, if you wanted to be technical, you would call a Green's function approach. And all this means is the Green's function is a response of a dynamical system to a sharp impulse. So let's imagine that you had something that was more or less a delta function. So at very early times, you just perturbed the densities of every constituent in the universe together: dark matter, baryons, photons, and indeed neutrinos, and then let them go. Good, okay, so this movie will show those different constituents moving. At early times, the most energetic neutrinos go at basically the speed of light. The blue and red, the gas and photons, are glued together by Thomson scattering. They move up to the speed of sound, which is 1/√3 slower. The dark matter, if it's cold dark matter, has no velocities at all, but the radiation dominates the gravity at this early time with a redshift of 5,000, and so its gravitational effect will drag the dark matter in its wake. And that continues to happen Here we are at redshift of just 2000, just before last scattering. And last scattering happens, it's the last scattering. So that means that the coupling of Thomson scattering of baryons and photons is breaking down, otherwise the microwave background wouldn't be considered to originate at that redshift. So when we get to about 1000, what you should see is that the blue and the red start to separate. And there we go. Okay, so now the photons can move at the speed of light, and off they go to infinity, leaving the poor old baryons kind of stranded. Now, thereafter, now that the photons and their pressure effects have left the situation, what's going to happen? We only have really the baryons and the dark matter in the universe, and they're just attracting each other by gravity, so they should fall together to make a joint common distribution of density. And that's what you see. So the dark matter gains a peak out here at 150 megaparsecs. The baryons get a reduced amplitude of peak, and by redshift of 10, they're not quite falling back together again, but they're pretty close. Okay? So the beautiful video, you can learn so much by looking at it. So let's do it again. All right, so this is the evolution of the delta function. There are no delta functions in the mass distribution, but as usual you can think of a general mass distribution as a superposition of all this. So what this shows you in an intuitive way is that the mass distribution at 8 scales should have a correlation function that has a single, relatively sharp feature at around about 150 megaparsecs. And since the power spectrum is a Fourier transform of the correlation function, you should see a number of oscillations corresponding to the Fourier transform of that single sharp feature. Just jump ahead. That's exactly what we do see, and this is now relatively old now. God. Relatively old data from the BOSS survey. This is the sort of thing that DESI is going to improve by an order of magnitude. But you can see the sharp peak in the observed galaxy correlations, and if you go to their power spectrum, you can see a number of oscillations representing the Fourier transform of this. So you can measure the baryon effects in large-scale structure, independent of whether you're operating in correlation function or in Fourier space. All right, so here's a more detailed expression for the acoustic horizon. So here it is, 145 megaparsecs, but it changes slightly with the density of the universe and the baryon density. And that's because it's an acoustic horizon. It's how far does sound waves propagate by last scattering. And so the speed of sound depends on both the baryon density, because when the photons and the baryons are strongly coupled, the photons provide the pressure, the baryons provide the inertia. So the lower the baryon density is, the higher the speed of sound, the closer to this ideal seal on root 3. And the total density governs something about to do with the time scale. So the higher density of the universe, the faster it expands, and so the less time there is for sound waves to propagate. And we understand very accurately the dependence, these parallel factors are just an approximation. It shows that things are actually very weakly sensitive to the baryon density, rather more sensitive to the overall density. And then it's just a word about that. Somebody somewhere at the start of this course should have defined the density parameter for you. And if not, better late than never. So what this means is that the actual density of matter is proportional to the density parameter times the Hubble constant squared. So we very frequently see this combination here, density parameter times Hubble constant squared. And of course this little h you know is, again, too late to be defined this way, but little h is h0 divided by 100. So that parameter combination arises whenever something is sensitive just to the total density, which the time scale of the universe is. And here's the total baryon density. Good. So we observe in the principal acoustic peak in the microwave background this length, this acoustic length, at the distance of glass scattering. A good approximation to that is glass scattering is 6 gigaparsecs away with a little h to the -1 scaling. Because as we saw, all distances in cosmology have a 1 over Hubble constant scaling. And empirically, there's a density parameter of the -0.4. So that's a very accurate formula for how far away the microwave background actually is from us. So you can calculate the angle that this subtends, S divided by D. And this is something that we observe with 1 degree. So what does that tell us? It gives us a constraint, assuming that the baryon density can be estimated by other means, for example, from primordial nucleosynthesis. We know this number pretty well, and there's not a great sensitivity to it. So fixing S on D, given that both of them depend on the density and the Hubble constant in different ways, gives you a constraint between the density and the Hubble constant. And pretty accurately, it's a simple formula. The density parameter times the Hubble constant cubed is known. So if we know anything from the microwave background, we know that number, and the error bar on it is almost negligible. So in short, the microwave background tells us rather directly the Hubble constant if we know the density parameter. So we're saying that H is equal to some number, the observed number, divided by the 1/3 power of the matter density. So you need to know the matter density, but not so precisely. And where does that come from? The microwave background can determine, or an estimate directly, an estimate of the density of the universe by the different amplitudes of the different acoustic peaks. And that's just schematically. I wish I had a zloty for every time I've drawn this. If you change the density of the universe, but keeping this degenerate combination the same, so that these peaks don't move sideways, what changes? What changes is the relative amplitude, and it's a more complicated scaling So the different amplitudes, the different harmonics will be altered as a function of the density. And why that is because of a strange coincidence. We know that the microwave background comes from a redshift of 1100. We know that the redshift of matter radiation equality is something like 3000. So by the time of last scattering, the universe is matter dominated, but not by very much. The energy density of radiation is still significant. Okay? So, so we can say that rho radiation over rho total at our scattering is some function of the total matter density. The lower the matter density is, the more radiation dominated the universe is at last scattering. Agreed? I need you to say yes.
Yes.
All right. Or no, let's say something. Right, now that coincidence sounds like an awkward combination, a complication. You would rather the universe was just completely matter dominated or completely radiation dominated. But it's actually useful because if you follow the evolution of gravitational potential fluctuations, they know about the equation of state of the universe. So if you take a given Fourier mode, it doesn't matter which one, and say let's have the amplitude of the gravitational potential perturbations in that particular mode versus time, then there are three phases. It's constant until the universe ceases to be radiation dominated and becomes matter dominated, and then it changes because of that change in the equation of state. Then it's constant again, and it stays constant forever until the universe becomes dominated by the vacuum. And then those primordial potential fluctuations are progressively damped away, and we're here. So around the time of last scattering, there's a non-zero phi dot. And right at the start of the lecture yesterday, if your brain wasn't completely fried, you might remember that there's a thing called the integrated Sachs-Wolf effect that depends on potential perturbations. So there's a thing called early ISW, which is here. And that's as distinct from late W, which puts large-scale perturbations on the microwave background. And that's from evolution of local large-scale structure. So it's this effect, and the fact it's happening around last scattering, that builds a small density dependence into the fine structure of the microwave background and breaks this degeneracy. Okay, so back to the story. If we think we've got some idea of the density from the relative amplitude of the acoustic peaks, then we can read off a Hubble constant. But the principal thing is this degenerate locus, and the effects that are breaking it are really quite small. Okay, so you should have much more confidence in the omega h cubed combination than you have in either of them. But in principle, the microwave background breaks both of them. I just comment briefly here that the acoustic peak we see in large-scale structure is ever so slightly larger than the one at the microwave background, because there's still some evolution in the propagation of sound waves after last scattering. So for high precision, it's important to not confuse those two acoustic lengths, even though they are both pretty close to 150 megaparsecs. Good, okay, so I didn't show this picture, so just wrap it up. This is the BAO signal as seen in BOS. So now we're looking at the correlation function in redshift space. So this is transverse separations, these are radial separations. And for the reasons I gave you before, radial distances are messed up by peculiar velocities. So the small separations, these contours are not at all circularly symmetric. But when you move out to the 100 plus megaparsec scale, you can see in all directions there's this ring of additional correlation, and that's the Baryon acoustic oscillations. I showed you this before, when you just average in direction. So this now becomes very interesting, because we have the same sort of arguments as in the microwave background. We have a predictable acoustic length, which on this plot is called R sub S, whereas here I just called it S. S for sound, either way, I guess. And we can, in a given galaxy survey, that can be detected, and therefore, in effect, you can measure, as with the CMB, the angle that it subtends at a different redshift. So this plot shows a range of galaxy surveys going from 60F galaxy survey at redshift 0.1 out to, particularly BOS, going out to nearly a redshift of 0.8. And as the text here says, in the standard cosmological model, you should be able to predict what that angle is, because you know the cosmological parameters are blank, and so you can calculate what the sound horizon should be, and calculate what the cosmological distance to a given redshift is, and predict the angle. And it goes well through the data. So the BAOs are very precise, and they give a good validation of the basic Planck model. So this is actually a bit similar to the supernova Hubble diagram. It's actually more accurate. And you don't even need to do it in galaxies. You can do it with quasars. That means you can measure the same acoustic feature in the correlations that we see in the Lyman alpha forest with the absorption in intergalactic medium. So you can combine the BAO data actually. So you can measure two different things. You can measure this distance, which is the transverse angle of the BAO scale subtends, and you can measure this distance, which is actually the offset, the radial offset. So that would be an offset in redshift that these correlations operate over. And you can predict this transverse and radial separations separately. That's the red and the blue line, and the data allow you to separate them, and so both transverse and radial parts agree pretty well with the default prediction. So it's really beautiful stuff, and it will get much better with DESI. Why have I told you all of this? It's because the BAO actually gives us an additional constraint independent of the microwave background. Because it's the same sort of argument as the microwave background. We have a theory predicts the acoustic horizon, we observe it at a given redshift, and you see what angle it subtends, and that should put constraints on the Hubble constant versus density parameter line. And that's what these ellipses here are showing. So actually they aren't pure Baryon oscillations. It's also in combination with the supernova Hubble diagram, which, as I emphasised, doesn't tell you directly anything about the Hubble constant, but it does tell you, its curvature tells you about the density parameter, so it helps squeeze in. Actually, I think maybe the pure BAO constraints are this dotted ellipse here, and the coloured ellipses are, you can rule out the highest densities when you bring in the supernova data in addition to BAO. But mainly the BAO dominates the precision. So it's interesting to combine that with a completely independent observationally, although it's the same method, the observation of the acoustic scale. This narrow blue thing is the omega h cubed degeneracy from Planck. Right, so Planck claims that degeneracy is broken, so the preferred value is close to the density of 0.32, so it's like there. All right, and you can see that there's the possibility of asking Planck to bend. And if you want a higher Hubble constant, as the external data on settings very much do, it does, you need to move along the axis in the direction of these external measurements. And if you're allowed to move as far as a density parameter of 0.24 or so, you could reach a Hubble constant of 73 and all will be well. But there are several buts. First of all, Planck would claim that this blue locus closes off at its upper end. Even if you chose to perhaps be a little distrustful of Planck alone, the BAO measurements, which are completely independent, also impose a horizon up here. But it's interesting, nevertheless, to me, that this idea of thinking that the true universe has a density parameter that's lower than the headline quoted Planck figure does some good things for you. So if you're able to move a little below 0.3, certainly being consistent with the BAO constraints, you can get the Hubble constant up to 70 or so. Planck claims that you can't go much beyond 69, but 70 becomes possible. Now remember, we had, with axial tension, we had a gap of 67 to 73. And the question is, do you need some new physics, a change in the cosmological model to close that? And I think the answer is yes. But on the other hand, what you can see is that if the Hubble constant was 70, that would be fine from the point of view of the BAO. I also emphasised that sort of Hubble constant fits the lower density parameters that gravitational lensing want. So there's a kind of attractive picture that I found myself drawn to of saying that you really want to think about the true universe being as far to the left as you can get away with, which means perhaps a Hubble constant of 70 or so. So I think there are two ways forward. The boring one is to say that there are some statistical issues with the data, which mean that the true Hubble constant is about 70, and there are small systematics that are pushing Planck away from it in one direction and the Cepheids away from it in the other. But neither is that strongly inconsistent with 70. But if you really insisted that this error bar continues to shrink and nothing changes from 73, then you have to have some new physics. And in a word, that new physics has to be something that changes the acoustic scale. Because these inferences on the Hubble constant versus density plane are built entirely on this idea of the acoustic horizon and the angle that it's attempts. And as I showed you, that acoustic horizon is set at very high redshifts. Let's look at it again because it's so pretty. Right. So the acoustic horizon is set when scattering stalls, photons disappear, the baryons are left becalmed. When that happens, we saw at a redshift of around about 1,000. So it's set at early times. So you've got to do something to change that number of 150 odd megaparsecs, and that has to be done early on. Okay, so I'm not going to go through many papers on the archive that talk about various additional ingredients. Early dark energy is the one that people appeal to mostly, that might alter the acoustic scale. The important thing is to be aware that it's that number that needs to be moved from its default value somehow in order to take these contours and move them up so they're set at 73. All right, so I'll make a few kind of more philosophical remarks at the end of this. Should you look at the current state of these cosmological tensions and think that you are strongly motivated to spend your career working on this hypothetical new physics? Well, I've shown you the kind of statistical evidence. The density tension, I pointed out that you can tune a value of the density parameter of about 0.29 that's in roughly 95% confidence consistently both with Planck and with the lensing data. So that's not a substantial, it's a substantial but not a glaring tension. With H0, the statistical evidence is stronger, so that statement's more about the lensing side of things. But the trouble is, the older you get, the longer you've seen the standard cosmological model work without new ingredients. You can ask, over the 40 years that I've been working in cosmology, what has been the real radical upheaval? Of course, you would say it was the acceptance of an accelerating universe in the 1990s. Before that, people were pretty well convinced that lambda would not be important. So they might say that's one radical new ingredient in 40 years, but actually it wasn't a new ingredient because of course Einstein invented lambda before there was any data. So lambda was a known piece of the theoretical landscape. And it wasn't introduced specifically to explain the evidence for the accelerating universe. Whereas what we're now saying is we have a standard cosmological model that doesn't quite work. And people are scouting around to try and invent some new ingredient that had never previously been thought of. Now we've never done that in cosmology, at least in 40 years. So you should be pretty skeptical about doing that, because it clearly doesn't happen very often. So if you're a Bayesian, which everybody in science is to some extent, if you have a prior level of belief in your head about the likely truth in a given situation, when you've seen new physics come into cosmology, almost never, but you've seen people make mistakes with their data and their error bars all the time, your gut feeling tells you which of these explanations is more likely, right? And also, another way to deal with this issue, if it's seeming contrived to invent a whole piece of new physics to explain one statistical conspiracy, is to say you would have greater confidence in a claimed new physical ingredient if it was designed to solve one problem and then by chance it explains something else that it wasn't meant to do. This is one of the reasons that despite the fact we have no final proof that inflation ever happened, people are kind of kindly disposed towards inflation, because inflation was invented to solve global cosmological problems. How do we get a universe that's expanding and is very close to being flat? 2 years after inflation was introduced to allow you to understand how that situation could come about from non-fine-tuned initial conditions, it was realised that it also predicted that there would be residual fluctuations in the universe from quantum processes. Right? And that, it wasn't meant to do that, it just happened. And that has the feeling of truth, right? When something unintended also emerges from a theory that turns out to match something else that we need to explain, which is why is there structure in the universe. So I'm kind of kindly disposed towards inflation, but I still want to see it actually verified, and it would be the detection of primordial gravitational waves that would do that. So is there an analogue in this situation of kind of high redshift versus low redshift cosmological tensions? And I think there is, but it's not in favour of the theory, because it's in favour of systematics, as I said. The data tell you that you want to push yourself towards a lower density than the Planck omega matter of 0.315. Doing so automatically forces you to have a higher Hubble constant because of this acoustic peak degeneracy. Right, so they're combined, so making Planck consistent with the lensing data, which bear on the level of inhomogeneities, automatically pushes you in the direction of a higher Hubble constant than the headline Planck 67, and therefore closes the gap with external Hubble constants. So to me, that has the feeling of truth, because this argument for lower density in the lensing world was made without regard for what impact it would have on the Hubble constant. So my predisposition then is to ask just how robust is this weak breaking of the very precise acoustic HQ degeneracy with Planck. So I made the following little investigation. So here is a residual plot, so we're not looking at the temperature power spectrum any longer. What we're looking at is the difference between the Planck data and a fiducial cosmological model. And so what is the fiducial cosmological model? It is the preferred 2018 Planck model, that is the one with a high density and low Hubble constant. And so, those residuals scatter around zero pretty convincingly. If you insist that the Hubble constant is actually 70 rather than 67, and do the same subtraction, so this is difference the h equals 70 model from the h equals 67 model, you get this green line, which to the eye doesn't actually look too bad in the Planck data. And in some ways, you see this, the biggest feature is this rise at here at 250 and this dip at, 800. It actually looks like the data prefer that. And indeed, it's known that if you fit only to the CMB data below L of about 1,000, the preferred Hubble constant is higher. So the evidence for a low H0, that is for breaking the omega HQ degeneracy in the direction of high density and the low H0, comes from the high Hubble data. And you can see the points that are doing it. There's 3 points here, it's out of about 1,300. You can see that they're, even relative to the fiducial model, they're slightly high. So when you go to a higher Hubble constant, and you're starting to pull things down here, that offset to those 3 points is disfavored. There's this point here, which doesn't really match anything, but when the green line goes up above zero, it dislikes that even worse. And there's a group of 4 points here, which again are disfavoring a slight dip that the green line has. So the worry I have when I look at this is that you realise there's only a small number of data points that need to change by a small amount. If I can take those 3 points, move them down each by 1 sigma, similarly with say these 3 and this one up by 1 sigma, those changes would be statistically inconsequential. 2 sets of data points would be well consistent with each other, but suddenly h of 0.7 wouldn't look so bad. So what you have to ask is how robust are the CMB results, which means looking at an alternative analysis. Well, that's the 2018 result. Okay, so I'm going to show you the same thing, but the error bars at small wave numbers are substantial. So it's, as I said, it's understanding what's going on here that matters. So let's look at high L. And I've also taken a ratio to cosmic variance. Maybe a few words about that would be useful. I've mentioned a number of times that there's instrumental noise in Planck. It's non-negligible. But even if you have an ideal map of the sky with 0 instrumental noise, there's still uncertainty. And that's because it's this business of ensemble averages. The theory that we have is an ensemble average power spectrum, but the sky is only one realization. So, here we go again. If you pick a given L value, how many wave modes are there in this? Well, this is over the curved sky. These would be thought of as labeling spherical harmonics. And you should know that at a given L, there are 2L plus 1 modes. So you can be pretty confident that you can't measure the power, so the fractional uncertainty in the power is going to be just limited by, because each mode gives you an independent estimate of the power, but each one fluctuates, and you average that down, and the more modes there are, the more precisely the power is measured. So this is like a 1 over root L effect. So high L, you can measure the spectrum very precisely. Low L, you can't. You never will be able to. So I've ratioed to that cosmic variance. But it's quite useful because you can see then, if we had a perfect experiment, all the error bars would be 1 in these units. Because by the time you get to L of 2000, they are 4. So that dramatizes how noise-dominated Planck is. So one future experimental improvement, which will come from ground-based experiments, and the ACT results from this November should also bear on that, could give us cosmic variance limited results right out here and shrink these error bars. That would certainly help. Okay, but otherwise, I'm just representing again this same thing. The Planck 2018 data with the fiducial Planck model subtracted, and also the green line is Hubble constant of 70 with the fiducial Planck model subtracted. So now let's look at different instantiations of the data. So that's the 2018 measurements. That was what Planck published in 2015. So that doesn't look too bad, right? Here are our particularly problematic 3 points. And you can see that between 2018 and 2015, actually things got worse. That is, they moved green to red a little bit away from H0 of 70, so disfavored it slightly more. But the shift is a fraction of an error bar. And that's the sort of thing that gives you a warm feeling when you redo the analysis, change the analysis pipeline. One of the detailed assumptions, and things move by a fraction of a sigma, then you start to feel that your errors are robust. However, there's a lot of complicated stages in the Planck processing, and many of which were in common to the 2015 and 2018 data. So there's an interesting project which goes under the name of EndPipe. I don't know if that's supposed to be an acronym, but it was an effort to go right back to the original Planck time-ordered data and just recreate with independent software, independent set of people, a whole chain of analysis, from estimating the Planck beams, trying to calibrate the analog to digital converters, rethink the corrections for galactic foregrounds. And they recently published particularly George Stathiou, who was, of course, one of the leading lights in the whole Planck project, recently published a paper with that reanalysis. Here's the archive reference. I encourage you to check this out. And now what you see is not so reassuring at all. And it's that these problematic points at LF 1400 have moved by more than one sigma, and actually now right on top of H not equals 70. There are even bigger movements at larger L. So when I look at that, this is a big problem for all of us in cosmology, because every experiment is moving in the direction of being like Planck. It's a huge edifice. It involves many hundreds, 1,000 people, each expert in some little bit of it. It all has to be put together. No one person has oversight of the whole thing. All we can do, whether you're in the team or like me, just an outsider looking in, is just try to make your own assessment based on this sort of summary evidence. And what this says to me is I'm not yet convinced at all that Planck has been able to break the omega h cubed degeneracy well enough to rule out a Hubble constant of 70. So that's my kind of, shall we say, boring and conservative viewpoint on it. But as I explained, Planck phase zero drives you inevitably to the idea of being skeptical that the data are completely precise and free of systematics, and always to look for evidence of that kind of softness rather than reaching immediately for new physics, because it's too easy to do that. So that's really all I wanted to say. To summarise it once again, that CMB lensing, I think, is in this fascinating position. It's already revealed itself as a competitive, powerful cosmological constraint, as strong as many of the other things that we know about. But by the end of this year, it will be almost in a leading position. It will be the CMB and ACT CMB lensing, and everybody else can go home. But even today, the lensing combinations that we have seem to favour a lower density universe than the headline one that comes from Planck. And to me, that has this appealing quantity that inevitably wants you to have a higher Hubble constant. And so, for now, my assumption is that the true parameters of the universe that we live in are a Hubble constant, say 69 to 70, density parameter of 0.28, 0.29. And as far as I know, there's nothing that contradicts the idea that lambda CDM with those parameters really is the true cosmology. Now, it'd be tremendously exciting if we get definitive evidence that that's not the case, in which case there'd be a whole new area of cosmological inquiry to open up. And I think everybody's terribly scared that that won't happen, and that actually this is the subject has converged, and in 1,000 years this is still where we'll be. But anyway, it's exciting times, because as long as the data keep roaring ahead, as ACT lensing will be, and as DESI large scale structure will be, we'll be able to decide which of these alternatives is correct. So, exciting times. Keep your eye on the archive, and thanks for listening.
Please. Why do you think I ask? When you say new physics, do you mean beyond standard model of particle physics or beyond lambda CDM?
Beyond lambda CDM. So, as I said,
there is some possible to explain using some extravagant model of the energy
so
method.
I emphasize that if you want not to appeal to statistical systematics, you need to alter the acoustic horizon. So you need to change the speed of sound as a function of time, or the scale factor as a function of time. You're going to change one or other of them, or maybe both. What people tended to focus on is the expansion history. So in the standard picture, you just plot densities of everything, and lambda is constant, and dark matter is subdominant now, but dominant at last scattering by a lot, by like a factor of 1 billion actually. Radiation is subdominant to everything today, but will rise faster, becomes close to dark matter at last scattering, and then takes over early. So that's the general sort of picture. So early dark energy hypothesizes that effectively the lambda curve does something like that. So you alter the expansion, you change the total density of the universe near last scattering, you alter the expansion time scale. I mean, you can do it, but it's obviously rather contrived is it natural that a model would have a particular bump like that? Obviously not. You can invent additional, now if you want to go with a particle physics solution, you can invent additional particles. So the speed of sound comes from scattering of electrons and photons. So if you have some additional particle that decays just around about last scattering, you can change the photon content just around that time. You can alter the speed of sound. So there's all sorts of, if you're allowed to have new physics in full generality, there's so many possibilities. Thank you.
Question, please.
Thank you, John, for a very nice lecture. Of course, much more students ask the questions, and maybe we can provoke some more discussion. So I have a question and a comment, actually. So, well, you can maybe read off the comment. So would you agree that manipulating the density parameter will fix the H0, make it a little bit closer to what supernovae data gives you, but it won't solve the acoustic horizon problem, because I think we have reclancing measurements independent of supernovae calibration of intermediate redshifts of just acoustic horizon. And this, this stays the same. So you actually rescale the equation to get H0, but the acoustic horizon stays the same. So this would be my comment or question, and the question would be, do you think that S8 tension from reclancing is related and can point us together with H0 to the new physics?
Okay, let me Let me see if I understand your point. I mean, as you said, independent of the CMB, we have this beautiful result that the acoustic horizon that we see in large-scale structure defines an absolute distance redshift relation. So that fact within the compass of the standard model means that we can't move. If we're just willing to go along the CMB degeneracy direction, we can't move along that green line indefinitely because the Baryon, the BAO Hubble diagram cuts us off, and the supernova Hubble diagram cuts us off. And within the standard model, that's correct. That's why I'm willing to tolerate a Hubble constant of 70, which puts us kind of here, but not 71 or 72, because then you have to violate the CMB and the low redshift BAO. On the other hand, if you introduce new physics that changes the acoustic horizon, well, it will. I mean, it doesn't change the. It doesn't change the data. Right? I mean, these data points are the same, but the curves to fit them would then have to have other cosmological parameters, and you could fit it with H0 of 73. That was the point.
Yeah.
The distinction you're trying to understand.
What about the state and tension?
Well, I gave you my take on it. The S8 tension is, I think, a density parameter tension. So, if I'm allowed to go to higher Hubble constant, then within the standard picture and with the CMB results, that definitely wants a lower density parameter. So actually, in advance, as soon as you heard about the H0 tension, you should have been saying, well, if I take this indication for a higher H0 seriously, I should be looking at the CMB and saying, can I get away with a lower density? And then if the lensing results come along and say, hey, we want a lower density, it's all pointing in the same direction. This may blow apart, and I wouldn't entirely rule it out. I mean, let's bear in mind, if George Staffy was here, I mean, he's a very strong defender of Planck, and it's, for good reasons. The Planck analysis is incredibly thorough and detailed. And he might well say, well, here's the Planck preferred cosmology. Total CMB lensing is in very good agreement with that. These low redshift lensing measurements are dubious because they depend on photometric redshifts, which are hard to calibrate with extreme precision. So, would I bet my house that future tomographic CMB lensing results and future galaxy shear might not move up to here? It'll be interesting to see. At the moment, it makes a nice picture, but anything, even the CMB, as I indicated at the end, you have to keep repeating it, doing it a different way, and demonstrating that things are completely robust. And obviously, this is a kind of state of the art, but people will carry on trying to do these things better. So if that were to go away, then these are the kind of divergent possible futures. It may well be that better understanding of photometric redshifts, more precise CMB lensing data, push us back up on top of Planck. And then you would have to say, okay, the ball is then in Hubble constant's court. But now they've got to move. At the moment, you see, it's more or less 73 plus or minus 1. So if the true value is 70, that's a 3 sigma discrepancy, which should never happen. But on the other hand, it doesn't need a big systematic before it's actually understandable. But then if you're back trying to bridge 73 to 70, 73 to 67, especially if the error bars on the absolute distance scale continue to shrink. If eventually we reach the point where it's 73 plus or minus 0.5 and everything congeals around about 67 from Planck, you would have to go for one of these radical solutions. But I just don't think we're there yet.
Hello. I have a rather rookie question. When you, because I'm a data scientist, not a physicist, but you have shown us the data robustness from Planck at the very end, right? And how it relates to cosmological model. In my intuition, the model fit with the data is rather wrong. I don't know if you can correct me, but as the very latest slides, the fluctuations in part spectra, right? In the plot where there was this residuals with scales like cosmic variance. Does it mean that Planck data is somehow included? I mean, the green line is a prediction, right?
Well, yes, or rather, it's the difference of two predictions. It's the theory. It's the theory minus the theory changing the Hubble constant.
Oh, okay. So I don't feel like this prediction difference really fits the data, to be honest. Could you please comment on this? Is it something wrong with the models we compare, or is it rather the data that is somehow off?
Well, that's what we want to know. What I'm doing is showing you different means of calculating the raw data and showing that they give results that move by amounts that are comparable to the kind of difference in theory when you perturb that parameter, the Hubble constant. Now, as to whether things are not good, let me see if I understand you. Forget the green line. Okay, so there's another line on there implicitly, which is a horizontal line at 0, right? Because this is it's a residual plot. It's taking the data, subtracting the fiducial cosmological model, the high density, low Hubble constant one. Are you content those red data points are all consistent with 0, or are you saying it doesn't look, even that doesn't look right?
Well, I'm not sure.
I mean, in a chi-squared sense, I think it's fine. There's this one. So that's probably the most discrepant point, isn't it? And it's only it's a bit over 2 sigma off, but out of 30 odd points here, that's exactly what you'd expect. So I don't think there's anything problematic there. The trouble is, the discrepancy with the green is not extreme. As I said, there's no point that's really badly inconsistent with the green data. It's just that overall there's enough slightly larger residuals that when you calculate a likelihood ratio, a chi-squared difference between these two, it's a delta chi-squared of about 10. Okay, so that's a likelihood ratio of e to the 5, so it's like 100 to 1.
Do you also agree that this doesn't take into account that foreground and background contaminations also contribution scales with the L can actually become important at very high L or dominant? So So
Well, of course, I mean, the best guessed background subtraction has been made, and Planck is in the unique position of having the widest possible frequency spectrum, which is one difficulty that these instrumentally superior ground-based experiments in the face, is that they don't have that wide frequency range, so they'll be more exposed to background corrections. But that's one of the things, I discussed this briefly with George, when you look at the N-pipe results, again, they have a different means of doing the background subtraction, and that may be contributing to the difference. Which obviously looks big. It's kind of unfair, because if you ask these shifts, how big are they? If I plotted the actual temperature spectrum, you can hardly see it move. So this is a very small fractional difference. But the trouble is these are the kind of deviations that we're trying to see if we believe now.
Do you think with the present or the near future technology, it is better to get down to better results than what Planck did 10 years earlier? So what with Planck we have anisotropies that measure temperature fluctuations down to 10 power minus 6. Do you think that we could better these results in the near future? And if we could, what can we learn from it? Is it just to constrain the cosmological parameters, or as you said, we are looking for some new physics in this?
Well, all right. Planck had, at least the high frequency bolometric instrument had, I forget exactly, but maybe 30 individual bolometric detectors operating at 150 gigahertz or so. Ground-based experiments now are going to have they have bolometric array detectors with currently I think in the region of 50,000 detectors, and each bolometer is more sensitive than a Planck bolometer. So instrumentally, what can be done from the ground makes Planck look like the Stone Age. That's unfair on Planck, because any technology that's put into orbit is always some generations behind, because it needs to be completely stable and understood, and it takes a long time to develop for space flight. And then you've got the huge advantages of being in orbit. There's no atmospheric foregrounds to deal with, and stability of the instrument in the way you don't get on the ground, and the ability to access extreme wavelengths, particularly the high frequency wavelengths and sensitive dust foregrounds, that we can't do from the ground. Okay, so instrumentally, the current generation of experiments are in a completely different league. The question is whether they then, it's always the same, you reduce your noise, you measure your noise to zero. The true uncertainty in your experiments are always limited then by systematics. So systematics would be the background corrections from the emission from the foreground, the foreground corrections, the emission from the Milky Way, and synchrotron dust signals that add to the CMB, and how well you can get rid of those. Assuming that can be done, well, you asked what will the future data bring us, and it should be able to sort out the shape of these potential small fluctuations at high L in the temperature power spectrum. But astrophysically, it will be incredibly rich, because the high resolution will allow us, particularly with the Sunnive's observatory effect, to probe in great detail what the baryonic amount of the universe is doing relative to the dark matter. And from the point of view of gravitational lensing, that is essential to understand that. So, I see that as one of the big things that the next generation of CMB experiments will give us, in addition to this just marvelously precise CMB lensing reconstruction map, which I still think will be the crown jewel of all this effort.
A question? thank you for your lectures. So I have a second question. As you know, I am not a cosmologist, so it's sometimes difficult to understand for me. How we estimate Hubble constant now if when the CMB was arised, Hubble parameter was another because
Yes,
yeah.
yes, it was. That's it. So the Friedmann equation tells us how the Hubble parameter changes with time, and it just says it's proportional to the density in the universe in various constituents. So the constants of the lambda, they're rising at a density, and the radiation density, and nothing else. Although, you know, it's something I've never mentioned actually, that it's also possible to add this term, that is whether the co-moving part of the metric is curved or not. In principle, that's certainly possible, and it was one of the long-standing achievements of microwave background studies, that in fact this term has got squeezed so that we know this thing has to be sufficiently small that most people are willing to assume it's exactly zero. Some analyses assume a precisely flat model, others do allow the curvature to vary, and that's included in the parameter constraints that are quoted. And you need to look at the literature carefully to see which it is. Whatever, in the standard model, there is a firm prediction for H of A. So if you measure, if you sort of say that that we are able to measure the Hubble parameter at our scattering, which at some level the Planck data do, it's an extrapolation to get H naught, certainly. But on the other hand, it's an extrapolation where there's no freedom apart from these few parameters. Right? And those are well constrained because H of A also goes directly into the distance redshift relation. It's just integral of C dz over H of Z. Right, so you can't really play around with extreme values of any of these parameters because they're constrained by the observations of distance redshift relation from supernovae or from the BAO Hubble diagram. So we know, effectively, we know certainly since the redshift of 3 what the distance Z curve looks like. So we actually know H of A during all that time empirically. So the extrapolation from Hubble, it is an extrapolation, but it's an extrapolation that's very well constrained.
Okay, thank you. And can you please show slide with evolution of density profile, dark matter, baryonic matter, and another? Yeah. Here, can you please
Play?
Yeah.
Say stop when you're ready. Oh.
So, my question is about how big influence of the dark matter distribution was in the early universe, maybe before CMB, because we saw more higher dark matter profile in the early universe.
Well, right at the start, I mean, the trouble is these curves are misleading because they were all scaled to have the same height to start with. Right, there was an equal spike in dark matter and baryons and photons. But you've got to remember that at this time, at the redshift of 10,000, the radiation density is hugely bigger than dark matter density. So this dark matter curve should really be this tiny little pimple down here. Right, so this just shows the kind of relative proportions. It doesn't show the absolute proportions. And so that's why, as I said, the dark matter is moving out, because the big person in the room is the radiation. You know, and they just move along, and all the little guys get knocked out of the way. So the dark matter just gets dragged along. But it is striking that it's only at the later times when the universe is matter dominated. And probably the other thing you have to remember is that the baryons are only like 5% of the matter. So the gravitational effect of the baryons on the dark matter is not so great. That's why it takes a while for the dark matter to be perturbed to the point where it acquires the BAO scale as it sucks the baryons in.
So we can assume that for very little bit higher redshifts than 10, in a gravitational lensing, more influence we can obtain on the small scale from dark matter, and in a local universe, for example, or redshift near 10, they are more equal. Dark matter
That's right.
baryon.
But you know, it's interesting that at redshifts that we're close to being able to access. So you know, we saw the archive the other day that my colleagues in Edinburgh claimed to have found a galaxy at redshift 16 in the GWST data. Yeah, it looks like a pretty good candidate to me, and everybody always hoped that JW would detect things perhaps beyond redshift 20. So 21 centimetre topographic mapping may be able to access those redshifts as well. This is a part of space, and I showed you that some fraction of the CMB lensing signal also comes from these redshifts. So this isn't fantasy, as once it would have been. You know, this is part of the history of the universe that we're going to be able to observe in increasing detail. And you can see there's a substantial difference, a separation between the dark matter and the baryon distribution at that time. And this is something that increasingly, I don't know if Vitek's going to talk about this, the simulators worry about setting up initial conditions in hydrodynamic simulations. That in the past, you just have dark matter and baryon particles, and you just perturb them in some uniform way. But you know, this separation needs to be taken into account. And that you know, given that the baryons are 5% of the total matter content, a factor 2 difference in the relative amplitude of fluctuations can change things by 1% on these sort of scales. And that sort of precision is going to be important.